Hello everyone. In this video we look at the case of inelastic collisions. Now inelastic collisions are those collisions which will be having the kinetic energy of the particles before the collision to be different from the kinetic energy of the particles after the collision. In most of the cases what we would have is there will be a kinetic energy loss, which would mean the final kinetic energy of the particles will be less than the initial kinetic energy of the particles. So we'll start with the head-on type of inelastic collision. Now when we look at the head-on collisions, these are the type of collisions which we can also call as one-dimensional collisions. So the particles will be having their velocities confined to a straight line, which means all the velocities of the particles before the collision as well as after the collision, the velocities will be confined to a straight line. So here we'll start with two bodies mass m1 and m2 which have their velocities u1 and u2 in the same direction. Now in all these results, if the velocities are in opposite direction, we would take the values to be negative, just like the way we follow the sign convention in case of the motion in one dimension problems. Now these two objects will collide, and after the collision like the final velocities are v1 comma v2. Now as per the definition of coefficient of restitution E, which is an indicator of how elastic or rather how inelastic a collision is, the E value will be relative velocity of separation after the collision divided by the relative velocity of approach, which means it will be v2 minus v1 by u1 minus u2. Now if we rearrange these values, what we would have is E is equal to u1 minus u2 v2 minus v1. So E into u1 minus u2 will be equal to v2 minus v1. Let it be equation 1. And of course every collision must satisfy the law of conservation of momentum, which would mean the initial momentum of particles before the collision m1 u1 plus m2 u2 must be equal to the final momentum of particles after the collision, which is m1 into v1 plus m2 into v2. Now the thing that we need to be considering is, already we discussed, in case of perfectly elastic collisions of head-on category, the value of E is going to be 1. But in this case, if we are referring to inelastic collisions, the value of E will be less than 1. And for all the inelastic collisions, the value of E is going to be between 0 to 1. So we'll take a look at that. But when we solve for the values of v1 and v2 from equation 1 and equation 2, what we would be arriving at is the values of v1 v2, which will be in terms of all the other known variables m1 m2 u1 u2 along with the coefficient of restitution E. So this is what will be the velocities of particles in case of head-on inelastic collision. Now since we are looking at the kinetic energy to be lost during these inelastic collisions, we can look at what will be the loss in kinetic energy. So loss in kinetic energy is going to be the total initial kinetic energy value minus the total final kinetic energy value. So how we can estimate it is, if we look at the total initial kinetic energy, it will be half m1 u1 square plus half m2 u2 square, the total kinetic energy of the particles before the collision, minus half m1 v1 square plus half m2 v2 square. This is the total final kinetic energy. Now we can substitute the values of v1 and v2, which we already got from the derivations of velocities of the particles after collision. And of course these values of the velocities will be in terms of the coefficient of restitution. So if we substitute the values of v1 and v2 in this kinetic energy loss expression, what we would be finally getting is the kinetic energy loss will be equal to half times m1 m2 by m1 plus m2 into 1 minus e square into the u1 minus u2 whole square. Now here let us pay a little bit more attention to this particular term 1 minus e square. If we are looking at a perfectly elastic collision, in case of the head-on category, already we have discussed that the value of E is going to be 1. If E is equal to 1, then we'll see that the kinetic energy loss, which is the delta Ke, in this case is going to be 0, because if you substitute the value of E to be 1, we'll get the delta Ke to be equal to 0. Now, in which case the kinetic energy loss is going to be maximum? So here, if we want to look at a value of E where the loss in kinetic energy is maximum, then the value of E must be equal to 0. If E is equal to 0, then in that case we will have the loss of kinetic energy to be maximum for a head-on type of collision, and that value will be equal to half m1 m2 by m1 plus m2 into u1 minus u2 the whole square. And this is what will be the condition for a perfectly inelastic collision in case of head-on category. So in case of head-on category, if we are looking at a perfectly inelastic collision, then the value of E must be equal to 0. And for the other inelastic collisions, the value of E will be between 0 to 1. So this is about the head-on inelastic collisions. We'll discuss more about this head-on perfectly inelastic collision in a while, but here we can keep one thing in mind, that for the perfectly inelastic head-on collision, the value of E is going to be 0. Now the significance of this is, if E is equal to 0, then if you look at the expression for E is nothing but the relative separation of particles after the collision divided by the relative velocity of approach of particles before the collision. If E is 0, that is possible only when V2 value is equal to V1, which means V2 must be equal to V1. That would imply that both the particles that we are looking at after the collision would move with a common velocity. So we can even say both the particles would stick together and move with a common velocity, and this result is of course only when we are looking at a head-on perfectly inelastic collision. We can have oblique perfectly inelastic collisions. In that case, we will look at a scenario where we have kinetic energy loss to be maximum, but in that case the objects need not stick together and move after the collision. So we look at one of the other common examples of the inelastic collision, which is rebounding of a ball after collision with the ground. Now let us say we are dropping a ball from a height h0 on a horizontal floor, and when it is striking the floor, the final speed with which it will be striking the floor will be given by the equations from kinematics. The final velocity or speed will be equal to v0 root of 2g h0. So this we will get from the kinematics relation, v square is equal to u square plus 2as. Now the initial velocity, since we are dropping it, it will be 0, and acceleration will be the acceleration due to gravity minus g, and the h, the height or h0 from which it is being dropped, the displacement is going to be minus h0. Since we are dropping it from a height, the displacement here will be taken as negative. In kinematics, we follow sign convention while using the equations, which is anything upwards we take it as positive, anything downwards we take it as negative. So the final speed with which it is going to strike the ground will be equal to root 2g h0. Now once it is striking the ground, what we usually see, let us say it is striking the ground with a speed v0, the speed with which it will rebound will not be same as v0. Let us say it is v1, so the speed of the ball after the first rebound. And if you look at the relation between the two, since we assume that the floor is always at rest, so floor we take it to be always at rest even before the collision as well as after the collision. So the value of E will be equal to v1 by v0, which is the relative velocity of separation after the collision, because the ball is coming away with a velocity or speed v1, divided by the relative velocity of approach before the collision, which is v0. So the coefficient of restitution for this collision will be simply v1 by v0. Now we'll look at what will be the speed of the particle after the first collision, or once it is rebounding for the first time, the value of V1 will be simply equal to E times V0, where E is the coefficient of restitution. Now the thing is, if the coefficient of restitution is high, the more close it is towards 1, it would mean that the value of V1 will be that much more close to V0. If the value of E is less, then the value of V1 will also be lesser. So V0 value is root 2g H0. So on substituting, we'll have V1 is equal to E times root 2g H0. Now if you look at up to what height it will bounce, because the practical observation that we have is once we drop from a particular height H0, after bouncing it will not be able to go to the same height, because the rebound velocity here is less. So let us say it is going to a height H1. So here H1, again from the kinematics equations, will be equal to V1 square by 2g. If you throw a particle with a speed u from the surface of the ground, then it will be going to a maximum height. H max will be equal to u square by 2g. So the maximum height the particle can go with this speed V1 will be V1 square by 2g, and V1 square is square of this, and on substituting the value, we'll have 2g and 2g will be getting cancelled. So finally H1 will be equal to E square into H0. So the results that we are having is V1 will be equal to E times V0, and H1 will be equal to E square times H0. Now on continuing this kind of a relation, we'll have the velocity after the second rebound, V2 will be equal to E times V1, and H2 will be equal to E square times H1. And continuing, we'll have V3 is equal to E times V2, and H3 will be equal to E square times H2, and so on. Now when we look at what is the situation after the nth rebound, the velocity of the particle after the nth rebound will simply be equal to E power n times V0, because if we look at after the second rebound, V2 is equal to E times V1. So on substituting, V1 is equal to E V0. So what we have is E square V0. So in the case of third, it is going to be E cube V0, and so on. And the height to which it will be bouncing will be given by Vn square by 2g, again by using the same formula of H max u square by 2g. What we'll have is the height up to which it will be able to rebound will be E power 2n times H0. So this is about rebounding of ball after the collision. And if it is a perfectly inelastic collision, then what would happen is once the ball is dropped, it will just stick to the horizontal floor. That is when the value of E will be equal to 0. And that's the case where we are going to be having maximum energy loss. Now we look at this perfectly inelastic collision in case of the head-on category. So if we have two objects M1 and M2 which are having initial velocities U1, U2, and after the collision we have seen that if we need to have maximum energy loss, then E value must be equal to 0. If E is 0, then it would mean that V2 value should be equal to V1. The final velocities of both the particles must be same. That means that both of them will be having a combined velocity or a common velocity. So here if we apply the law of conservation of momentum, what we would have is M1 U1 plus M2 U2 will be equal to M1 plus M2, because both these objects are going to stick and move with a common velocity, M1 plus M2 into V. This V is what we are calling as the common velocity. So V value will be equal to M1 U1 plus M2 U2 by M1 plus M2. So this is the final common velocity of the particles. And if you want to calculate what is the kinetic energy loss, the kinetic energy loss will be given by the initial kinetic energy of the particles, total value half M1 U1 square plus half M2 U2 square, which is the total initial kinetic energy of the particles minus total final kinetic energy of the particles, which is, if both of them are sticking together and moving with a common velocity, we can take both of them to be an object of mass m1 plus m2, and the common velocity will be v. So the final kinetic energy, this is the initial kinetic energy and this is the final kinetic energy. We can substitute the value of v from we can say this is equation 1 into equation 2, and thereby we will be able to find out what is the kinetic energy loss. So the significance of this head-on type of perfectly inelastic collision is that both the objects will be sticking and moving after the collision. And one thing we need to be keeping in mind, that we can even have perfectly inelastic collisions of oblique type. Let us say, for example, we have an object of mass m1 coming like this with a velocity u1, and another object of mass m2 coming at an orientation with a velocity u2, and these two may have a perfectly inelastic collision. Of course, solving the variables of the oblique collisions will not be easily possible, because in these oblique type of collisions we will be having number of variables, generally more than number of equations. But the point is, in this type of oblique collisions, the objects need not stick together and move after the collision, even if it is an perfectly inelastic collision. So this moving together is only the condition in case of the head-on type of perfectly inelastic collision. Now we'll just look at some sample problems. So we have two masses, 8 kg which is having a velocity of 10 meters per second, and 2 kg which is having a velocity of 5 meters per second, moving along positive x-axis. So both of them are moving along the positive x-axis. Undergo perfectly inelastic collision. What is the kinetic energy loss in this collision? So what we need to be looking at is, so 8 kg moving with a velocity of 10 meters per second towards the positive x-axis, and the next object is 2 kg which is also moving along the positive x-axis with 5 meters per second. Now after the collision, what would happen is, these two, the 8 kg and the 2 kg, these two would be moving with a common velocity. So to find the value of the common velocity, we will be using the idea of conservation of momentum. So always in case of this head-on type of perfectly inelastic collisions, to find the final common velocity, we will be using the conservation of momentum principle. So since momentum is a vector, here both these 8 kg as well as 2 kg are having the velocities in the same direction. So both the momentum values are in the same direction, so we can take both of them to be positive. Now the reason why we are mentioning this is, if the objects are moving in different directions, if one direction momentum we take it as positive, other direction we must take it as negative, because momentum is after all a vector quantity. So here the momentum of the first particle, 8 into 10, it will be 80. So we are not keeping units over here, because everything is already given in the SI system. And the momentum of the 2 kg particle will be 2 into 5, which is 10. This is the total initial momentum. And finally the 8 kg and 2 kg, total mass will be 10 kg, is moving with a combined velocity, let us say v. So 90 is equal to 10v. From here we have the value of v is equal to 9. Unit will be meters per second, because already all the quantities are in the SI system. Now when we want to calculate what is the kinetic energy loss, kinetic energy loss will be the total initial kinetic energy minus total final kinetic energy. So the kinetic energy of the 8 kg particle initially will be half into 8 into 10 square, plus the kinetic energy of the 2 kg particle will be half into 2 into pi square, minus finally both the particles are moving together, which means it is like a 10 kg particle which is moving with a velocity of 9 meters per second. So what we have is 2 ones are 2 fours, so 10 square is 100, so we have 400, and this is 2 ones cancel, plus 5 square will be 25. Then what we have is 9 square is 81. So 81 tens are 810 by 2. So 425, and over here it is 810 by 2, which would mean 405. So the Ke loss will be equal to 425 minus 405, which is 20. Unit is going to be joules. So the kinetic energy loss, because all the mass terms are in SI unit kilograms and all the velocity terms are in meters per second. So this is the kinetic energy loss in this perfectly inelastic head-on type of collision. Now we look at one more illustration where we have two masses, 6 kg whose velocity is 8 meters per second and 4 kg whose velocity is 2 meters per second, moving along positive x-axis and negative x-axis respectively, which would mean that the 6 kg is moving towards the positive x-axis and the 4 kg is moving towards the negative x-axis. So here the particles or objects, they are moving in opposite directions. So let us look at the situation. And of course, in this they are undergoing perfectly inelastic collision, and we have to find what is the kinetic energy loss in this collision. So we have a 6 kg block which is moving towards the positive x-axis with a velocity of 8 meters per second, and along the same line there is a 4 kg block that is coming, but the velocity is towards the negative x-axis and the value is 2 meters per second. Now after the collision, both of them are going to stick and move with a common velocity. I mean, we would not know whether they will move towards the positive x-axis or whether they will move towards the negative x-axis. We will come to know about it by knowing the sign of the value v. How? We will just take a look at it. So here, if we take the parameters along one direction to be positive, we have to take the parameters along the other direction to be negative, because we are dealing with velocities or momentum which are vector quantities. So here let us say the right side or positive x-axis we take it as positive, then the left side or the negative x-axis terms will become negative. So the initial momentum of the 6 kg particle will be 6 8s are 48. Since it is in the positive x-axis direction, we take it as plus. And the initial momentum of the 4 kg particle will be 4 2s are 8, but it is towards the negative x-axis, so we'll take it as minus 8, will be equal to, finally both the particles 6 kg and 4 kg are sticking together and moving, which means this is like a 10 kg particle which is moving with a velocity v. Now on the LHS, what we have is 48 minus 8, which is equal to 40, is equal to 10v. So here we have v is equal to, 10 1s are 10 4s are, v is equal to 4 meters per second, because all the other quantities are in the SI system. So this is the velocity of the objects, the combined velocity of the objects after the collision, and we are getting the velocity to be positive, which means both these objects will be moving towards the positive x-axis with a velocity of 4 meters per second. Now we have to find what is the kinetic energy loss in this collision. So the kinetic energy loss in this collision will be equal to total initial kinetic energy of the particles minus total final kinetic energy of the particles, half into 6 into 8 square, the initial kinetic energy of the 6 kg particle, plus half into 4 into 2 square, the initial kinetic energy of the 4 kg particle, minus finally both the 6 kg and 4 kg are moving together like a single particle whose mass will be 10 kg, half into 10 into the common velocity is 4, so it will be 4 square. So here we have 2 1s are 2 3s are, 8 square is 64, so what we have is 3 into 64, 2 1s are 2 2s are, so plus minus 2 1s are 4 square is 16, so we'll have 8 minus 80. So when we multiply 3 into 64, 3 4s are 12 and 3 6s are 18, so it will be 192 plus 8 minus 80. So what we'll be having is 192 plus 8 is 200 minus 80, which will be 120. The unit is going to be joules. So the kinetic energy loss will be 120 joules. And the general observation is, when we have the head-on perfectly inelastic collision between particles, if they are moving in opposite directions and coming and hitting, then the kinetic energy loss in this case will be generally maximum, like the example which we are seeing over here. So this is about the head-on type of perfectly inelastic collisions.